Hi, everybody, and welcome back to another episode of the Cloudology podcast. So today we're going to be talking about something that's very near and dear to my heart. Matthew and I were talking a few weeks ago, and he was very interested in, having a conversation about, hey, I know a little bit about big data, but I'd love to kind of dive into some of the history of big data and why, where some of these things came from and how things work, today. And, there we are, right? So the topic for today is going to be big data in a nutshell. A shout out to the old In a Nutshell technology books from the 90s and early 2000s, right? And so, on that, I have my co-host Jerome Francois here with us. So what's up, Jerome?
Hi. Hey, all good. Thanks for having me.
Absolutely. And if you want to go to the next, we'll find out how LeBron feels about this whole thing.
Yeah.
So this is the old. Everyone feels this way sometimes. This is the old LeBron cry face meme. Someone please tell me what is big data, right? The amount of times that I've, as a big data architect, as somebody who's focused the majority of my career on open source big data technologies, the amount of times that I've explained this stuff to customers, or the amount of times that I've had to talk people out of using big data, right? Because a lot of times these big data technologies aren't necessarily the right fit. But people just love to use them and want to implement them because it's the buzzword, right, et cetera. But Matthew, why don't you introduce yourself, and then we'll continue.
Sure. Yeah, so I'm Matthew Lombard. I'm the same team as you, Jeff and Jerome, the Oracle A team, focusing on data analytics. My primary focus is Fusion analytics as well as Fusion SAS data extraction. And I mean, that question, what is big data in a nutshell? I have a more data warehousing background, so traditional data warehousing. So I think it's going to be enlightening to get that question answered today.
Absolutely, and the one thing I will mention too is that you being here is extremely important. Having your kind of angle on this and the questions that you ask, because you're going to be asking questions from that standpoint of a Fusion background, a SAS background, and there's a lot of opportunities to leverage these technologies in the Oracle Cloud, like natively in Oracle Cloud today for our SaaS and FAW customers. So we definitely want to, highlight those as we talk through as well. So, Jerome, do you want to start with the 3 Vs maybe? Everyone knows about the 3 Vs. We can start there, and then we can move on to.
Yeah. So we often discuss about the 3 Vs for big data, being volume, velocity, and variety. So volume, because we've got a lot of data, probably too much to handle on traditional hardware. Velocity, because it goes fast, it could be real time, too much to process in batch mode. So that's interesting as well. And variety, because we've got some structure files, but also some structured format, but also some unstructured format. We've got emails, we've got things like that where you need to get the data, get some sense of your data by parsing the email or things like that.
Right, and I was going to add, for me, the volume has always been there. That drives a lot of the conversation. We'll talk about that. Velocity, everyone always wants real time, pseudo real time, even if they don't know how they're going to use it. But the one that really drove a lot of the big data opportunities that I've worked over the years has been variety, because while things like Oracle Database and Redshift and these new technologies that have come up now support a plethora of file types today, right? I mean, we're in 2022. In 2010, nothing supported anything, right? Like you could barely do JSON in a database. And so the variety piece actually drove a lot of big data implementations. I'm doing air quotes for those of us that are listening to the audio, that truly weren't high volume, that truly weren't high velocity, but they needed that support for multiple file types, semi-structured, unstructured data, all mixed together, getting a single view, a single pane of glass on that data. We see a lot of that as well. So that's definitely a big, I would say for me, the biggest of the 3 Vs is variety, as far as the amount of big data deployments that particular set of use cases and requirements drove.
Yeah, I agree. It's the 1V that was too much for traditional database, right? Volume, that was okay. Velocity could work.
You want to spend enough money, you can get the other 2 Vs.
Yeah,
right?
exactly.
Money thing.
But if you combine the 3V, it's too much. So there we are, big data. So it first started with the storage.
let's back up let's back up for the audio real quick and just kind of outline what we're looking at here.
Sure, yeah.
So we've broken down the kind of a traditional life cycle of data, right, for a data management layer or an analytics, use cases for analytics or data science, data analytics, right? You start at your source, you have your movement and your ETL layer where you're transforming your data. You have your storage layer, you have your query layer where you're going to be pulling data out, and then you have your serving layer where you're going to be taking that data that you've queried and kind of curated over the course of all these steps and provide that downstream to your users, right? So that's what we're looking at. From a source perspective, we'll start there quickly. Big data sources from anything, right? So multi-cloud, any database, flat files, applications, events, sensors. It really played a big role traditionally in the sensor space for sure, because you have so many different files coming in, and you just cannot process that in a database very efficiently. Right?
Yeah, social media as well.
That's right. Social media is another great one. You have streaming data coming from social media in real time and making decisions on things like that. One of the coolest use cases I've seen for these kind of real time things is around power plants. So a lot of electric companies, the price of power changes every 10 minutes. And so there's a user sitting at the thing looking at all these different metrics that are coming in on a real time dashboard that are a combination of weather patterns, what the stock market is doing, what these weird old file formats from these that are coming right off of people's power grids, people's power meters at their house, right? And it's that variety again, right? That combination that drives something like a Kafka deployment or something to provide that to a dashboard.
Yeah.
Right? So that's the source. And then Jerome, go ahead. So we're going to start with storage, because the reason why, even though it's not in order, storage is really the heart of where all this came from. Right?
That was the first main difficulty. It was to store all that data, right? Coming really fast, different format, and a lot of data. So that's why it really started, right? Everything started from there. And what Hadoop brought to the table is HDFS, so it's a Hadoop distributed file system. So instead of just having one large server where you would put all your files, here you could do that with some community hardware, some really cheap disk, but you would buy a lot of them, you distribute that, and you will replicate the data on a few different disks, different nodes. The story here was that you could just buy a bunch of second-hand computers and put them together into a cluster, right? We'll see a bit later on that it's not really what happened in the end, because people realized that buying some different things and really cheap computer was not that easy to maintain. But that's the idea, just to have a lot of cheap disks and put them in a cluster and replicate the data.
And the other part that happened over time was that the profile, the hardware profile of your cluster changed depending on what you were trying to do, right? So if you're running a highly intensive data science job with something like Spark, or one of the many, plethora of data science things out there, then maybe you need GPUs, maybe you need lots of RAM in that area, right? And if you're running a bunch of Hive stuff with really high volume stuff with Hive, then you just need fast disk access and a lot of it, right? So you don't care as much about RAM. So, the profile, right? The actual hardware itself, as these things got better and as we move through the history of all these, that also changed, right? And so, what drove it, right? What drives anything that we innovate? It's cost, right? So we were doing data lakes, we were doing Hadoop clusters, if you want to call it that. A Hadoop cluster is just a giant lake of data, right? We were doing this kind of thing in database from the beginning, right? People were bringing in different file formats, and maybe the transformation was a little more complex, but at the end of the day, we were, having some sort of data store in database. And as these databases got faster and better and stronger and more compute intensive, the storage prices just skyrocketed, right? And so that's where, this stuff came out. And I mean, obviously, this is all, for anyone who doesn't know, this all came out of Google, right? So Google is the company that, their engineers created what became Hadoop. They have their own internal version of this that they still run that's completely proprietary. But some Google engineers left Google and started these different, of all the open source technologies, there's so many that started as a Google like incubation project, right? for sure.
So Jeff, you talked about Spark earlier. What is Spark?
So Spark is a in-memory based set of tools for data movement and data extract, right? So we'll definitely get to that as we go to the data movement piece.
Okay.
So why don't we back up? The next thing I want to talk about real quick is kind of cloud storage, right? And like where things have gone today. So if you want to back up a couple, Jerome.
Yeah. So
I think like, you know, what happened, you know, Jerome, I'll let you take this one, but what happened after, you know, we had this commodity hardware. We ran Hadoop clusters on-prem for years and years. We had the storage. It was fairly cost efficient. You know, these things were great. But what was the next step for us, right? You know, moving forward as, you know, a collective, what was the next technological leap that we made?
The cloud.
That's
Move
right.
to the cloud. So naturally.
What's this
changed.
podcast called again? I forget.
It's called Cloudology, I believe.
Oh, okay. Well, that makes sense.
Right.
All right, that's good.
So yeah, with the move to the cloud, new deployment options were there. So Amazon S3 started with some kind of buckets, and we have something similar in OCI called OCI Object Storage, right? And basically that's the same. That's distributed file system for you, except that you don't have to manage a full cluster. It's all organized in buckets, so it's easier to do. But that's the natural evolution coming from HDFS to a cloud environment, right?
Very, very good. And I think it's much cheaper, right? Like obviously you have a huge cost savings.
Yeah.
It's pennies to store things in object storage compared to what you're paying to store these same things in an on-premise Hadoop cluster that you're maintaining all the disks, and Joey has to run downstairs and swap hard drives out anytime a node goes down. I mean, that maintenance nightmare was real for so many years. And people were spending so much money on maintaining and just keeping these clusters alive and well. And now with this new object store, and you know, we only mentioned Amazon. I know in our pre-conversation, Matthew had mentioned, what about Microsoft, right? Well, the reason why, Azure Blobs. So the reason why we have S3 here is that S3 really became the universal language, right? All these different clouds, storage layers speak S3, right?
Yeah, so they've got an API and everything else is compatible to the S3 API. So you can use the S3 API to query object storage as well.
That's right. And same with Microsoft, same with Google. All the storage layers kind of use that as a standard API entry point. Now, of course, everyone has their own, you know, proprietary layer on top of that can do different things, and you know, that varies greatly. But from a S3 perspective, that's why we wanted to call that out, because it was really the grandfather. And to be frank, the performance of S3 has just done nothing but skyrocket. It's a great performing technology. Amazon's done a great job there. Like they were, you know, they obviously were the leaders of that, and they've continued to innovate in that realm, and it's really, really good.
And what I like with this storage is that you can also archive things if you don't need it. If you don't think you'll need it in the near future, you can archive that, and it's a fraction of the price. It's even way cheaper. And you can still restore it if needed. There is some delay, but that's it. If there's some data that you don't need, unless you'll have an audit or something like that, you can archive it.
Absolutely. All right, well, let's talk a little bit about the next topic that Matthew was discussing, right? So first we're going to start with MapReduce. So historically what happened, right? We had all this data, we stored it at HDFS. That's great, okay? So now our data's sitting there, and then what's the next step? Well, somebody's like, well, now I want to merge this data in with data from my database, and I want to change the way it looks a little bit so I can do something with it. We don't have a way to do that, right? And so that's where MapReduce comes around, right? So MapReduce is a set of Java libraries. I won't get into the details. It's super confusing, and
it is.
The biggest problem with MapReduce, in my mind, is that unless you really knew what you were doing, there was a lot of opportunity to screw up and make something work very poorly, right? From a performance perspective, because you were shuffling data, you had very fine-grained control. I kind of liken it to C++, or you know, your traditional C language, and Java from a garbage collection perspective, right? You don't garbage collect in Java. Java has underlying stuff that does it for you. You don't handle your memory in Java. Java just handles the memory, and you can blow the stack. We've all done that, but you're not responsible for doing that. C++, C, you can handle all that. You have to handle all that. But then you get a memory leak on your computer, and your computer won't start up, which happened to me in college. So, you have with great power comes great responsibility. But all of the high-speed apps, all the gaming libraries, right? All that stuff is written in C because you need that fine-grained, fine-tuned access to the memory of the machine at a very low level to the GPU. Right,
for performance, for better performance.
For performance.
Yeah,
but you would never see good game. You'll never see high performing games written in Java, right? You'll see something like Minecraft that looks like my third grader colored it in, right? But you're not going to see something like Call of Duty Modern Warfare 2 running in Java, right? And that's how I liken MapReduce to some of these other. You had mentioned Spark. I liken MapReduce to that, right? You had to be very aware of what you were doing when you're writing MapReduce code.
It was low level. It was low level basically compared to what comes after that. So there was a need for something easier than MapReduce, and that's where Hive and Pig first came in, because they come with some new dialect. Hive has HiveQL, which is similar to SQL, that will then actually generate MapReduce job for you, so you don't have to.
It translates itself automatically
exactly
into MapReduce. So you're still using MapReduce when you use Hive, but then now they have Hive on Spark. So there's other like faster. They have Hive on Tez. We didn't put Tez up here, but another technology where you can do higher speed and stuff like that, right? But the idea is, people that were doing these jobs were not Java developers, which is what you needed to be a MapReduce programmer, right? They were DBAs, they were data scientists, they were SQL people. And so Hive provided a really amazing interface where you can say, hey, if I know SQL, the amount of CTOS statements that we've written in Hive over the years is crazy. And that's what I think is the big, and Hive has more production. There's more, like, of all these technologies we're going to talk about today, Hive has the most production deployments in the world today, right? Because it's just very easy to use, very familiar for people, and it's just very widely leveraged for sure. Pig not so much, right? So Pig kind of fell off for sure.
Sorry?
Yeah, go ahead, Matthew.
Yeah, so would you say that Hive brings kind of an abstraction layer on top of MapReduce?
It translates. So HiveQL is translated into MapReduce job for you. So you just write SQL, and then it will create some MapReduce job a lot easier. Same for Pig. Pig has a dialect called Pig Latin. It's more declarative than Hive, so you do step by step.
More of a programming language, right?
Yeah, you say, I want to filter something, I want to join it with something, so it's one step at a time, but it will do the same thing, create a map.
And Pig is definitely the grandfather of Spark for sure, because Spark has that same iterative type of implementation. And so that's big. We do call out Scoop here as well. Scoop was leveraged to pull data out of databases and put it into HDFS. So that's what the job of Scoop was for all those years. And Scoop was very widely used for every Hadoop deployment. I mean, Oracle Big Data Appliance, which we'll talk about in a little while, had some, proprietary things that worked with Oracle database that we wrote, right? Like OLH and what is it called? What's the OSCH or OCSH?
Yeah.
Anyway, it doesn't matter. Oracle Loader for Hadoop for sure, I remember. But then that's
OSCH.
OSCH was the one that went to the database. And so these were like, very custom and proprietary to Oracle. They used database dumps and stuff, right, to make things faster. But generally, Scoop, JDBC connection to any database, fairly performant to load data into your Hadoop cluster from a database. It was a huge player, so we had to call it out, right? For sure. And I guess the last thing, and again, remember we're talking about ETL and data movement here, right? Because the other thing I wanted to say is several of these technologies play a role across the board, right? Something like Spark can be talked about at every single one of these points, right? Real time, batch, it does it all, right? Spark kind of in some ways to their detriment is boiling the ocean, right? But also to their credit is boiling the ocean, right? So that's what makes Spark so good, and sometimes not as good as it probably could be in some ways, is that they do almost everything.
Yeah, they do a lot. Yeah, but
and
so
then you have something like Hive as well. Like Hive is all over the place. It's going to be a part. You could literally do your whole ETL layer in Hive. You could query everything out of Hive, and you could serve it to your end users in Hive. And you could do the whole, and that's not uncommon. That's something that we saw a lot, right? So Hive is another huge, piece of the puzzle.
And to answer your question from earlier, the difference between Spark and what we've seen above is that everything else is doing, reading everything from disk and doing a lot of operation read and write from disk, while Spark will do as much as possible in memory. So you'll try to have a lot of RAM on your cluster when you're using Spark, but that actually increased the speed of everything. It was a game changer. Spark was a game changer. So yeah, Spark is actually...
Yeah, go ahead.
Spark is actually available in different languages, so you can use it in Java, Python, Scala. So it also has a Spark SQL that we'll see a little bit later, but it's really easy to use. I think the strategy was good, to be present in different languages so everyone could adopt it. And
the APIs are simple, they're familiar, they're human readable. I mean, if you look at Spark code, it's like, object 1, filter on this, object 2, aggregate on these terms. I mean, the way that they design the way they design their APIs are very user friendly for these use cases, right? They were smart, and it's community driven project. I mean, obviously now it's owned by Databricks, right? But is it data? What are they called? It's the people who own Databricks also own Spark, but I don't know if that's the name of their actual
I don't know.
company. But yeah, so those guys that are doing all these different, very kind of innovative things with Spark, they own the project now. So it's still community driven, but it's much harder to become a contributor and actually contribute, right? It's very much driven by their organization, but very similar to what Confluent did with Kafka, for example. But it's still, in the old days that we're talking about, right? Like in the glory days, it was very much an open source project as well. And Spark has the most contributions of any open source project in the history of open source by like billions. I mean, it's not even close. Like it's not even close to the next one. So it was very much community and like crowdsourced and community driven as well.
Yeah.
So you store your data, you have cheap storage, you have data movement to get your sources into that storage. What's next?
We need to query it, right?
Back to the original problem. Like I just want to read the data out.
Here again, you've got Hive, because Hive is SQL-like language. HiveQL is a SQL-like language, so that's a good language to query, right? Impala is actually implementing the same language, but is better for querying. Usually they have better performance for analytics use cases. Do they use some in-memory as well, Jeff? I think so. That's the difference, right?
And that's the big differentiator for Impala, is it's in-memory driven. But it is different than like some of these other ones we've talked about, because Impala is part of, there is an open source version, but Impala became part of the Cloudera stack. Cloudera being the enterprise version of Hadoop that happened. So everything cost money, right? So you had to buy license to use Cloudera, but they did tune it pretty well. So a lot of Impala deployments that I've seen performed extremely well. And I think the downfall of things like Impala and some of these other, there's a million SQL technologies that have come and gone in the past, is Spark SQL, right? So again, Spark comes in, it works. Everyone supports it. Everyone understands it. It supports multiple different types of deployments. You can deploy it standalone. You can deploy it as part of a Hadoop cluster. You can use different languages. And so when Spark SQL is developed, and it's become very, very performant over the years as well, it's kind of what people have gravitated towards, right? And so again, it's not killing these projects, but you see so many deployments around Spark, and you see this kind of, we were talking about where we were, right? Where we were with these commoditized Hadoop clusters that people were building out, and a lot of maintenance involved, a lot of administration. We'll talk about that in a little bit as kind of like probably definitely the downfall of Hadoop, because Hadoop was very hard to keep up and running, right? That's the bottom line.
And expensive.
But then, and very expensive.
While you were looking for something cheap, in the end it would be
That's
expensive
right.
because of the
That's
maintenance.
Right. Way more expensive than anyone could have ever imagined to keep a Hadoop cluster up in production, right? But you have something like Spark that can stand alone, right? Spark can live as an elastic standalone service, a cloud native service, right? As cloud came along, and that's where we've seen so many of these workloads gravitate towards over the years, right? And that's why Spark SQL is really kind of obviously Hive, I think, still very well used and leveraged across the board, but I think at the end of the day, Spark SQL is going to be the outright winner as we move forward, in the number of customers using it.
Yeah. So with these languages, these tools, we can query data, but it's still based on the files, right? So we might want to speed that up by having an actual serving layer. And there are different options. Jeff, maybe you want to take Vertica?
Yeah, sure. So we talked a little. Jerome and I were talking a little bit before when we were putting these together, and there's a couple of different, like flavors of these type of serving layers, right? So there's these what we call columnar databases, right? Where you have the idea in a columnar database is that you have a single table view, basically, right? So it's a lot of columns. You can have thousands of columns, and then you have super deep amount of rows, right? And this type of database technology is built custom to handle that kind of view, right? Those are perfect for a serving layer, right? So like you can give every bit for analytics, right? Because the more data, the more columns you have available, the more different types of things that you can give to your user in an analytics view in a tool, the more things they can drag and drop and discover, and more insight they can discover, right? So that's your columnar. Then you have one of the things that we talked about was Cassandra and HBase. Those are a different kind of columnar, right? So they're still considered columnar, but they're more of like a key value pair store, right? But they're very fast. They're very fast reads, and that's what you're looking at here. So this serving layer, something like a Hive, if I go query Hive and I say, hey Hive, give me some columns, it's going to generate MapReduce and run MapReduce across my entire cluster. It takes forever, right? It's very slow. When I say, hey Vertica, I need data, it's going to have all this data warmed up, prepped up, sitting ready in a very fast access type way. But loading it, maintaining it, tuning it, much harder, right? So that's the give and take that you're looking at with these serving layers. Is what H-based clusters are a freaking nightmare to keep up and running and fast, absolutely nightmare, right? For example, so I got a little bit ahead of myself. I just was supposed to only talk about Vertica, but Cassandra and HBase, they run directly against HDFS. So that's kind of the difference between those and something like a Vertica, right? Vertica, you kind of load the data into Vertica, right? With Cassandra and HBase, they point to an HDFS store and they run from there, right? And so they will pull data into themselves and have hot, warm data and things like that, right? There's all kinds of tuning and indexing. The indexing is crazy that you can do, but both these technologies are very commonly used for being at the far right side of your architecture diagram and providing the downstream data for your consumers.
And how about MongoDB? Is it pointing to the file system, or is it do you need to move the data to MongoDB to be able to?
It's your turn, Jerome, if you want to go. But,
no, go ahead. I think you're better on MongoDB than I am.
So Pentaho, where I was previously
exactly.
a developer, we actually were partnered pretty closely with Mongo, right? We were one of the first ETL technologies to really kind of embrace this. And Mongo is a document store, right? So it again works on like a key value pair kind of paradigm, but it's less of a row column type database view and more of like a store or cache of documents, right?
No SQL.
And they did add SQL over time. They added joins, and if you go call Mongo right now, they'll tell you that they can be your enterprise data warehouse. But from the beginning, it was more of like an application type of database where you could easily, the thing about Mongo schemas is they're completely dynamic. An Oracle schema, you add a column, you're screwed. You got to go back, you got to deal with stuff. Your app might break, all kinds of stuff. With Mongo, they just don't care. You add columns, as long as you're not removing anything, right? You can add forever, no one cares, which makes it very friendly for development of a new app, right? Because on my screen, Jerome, Matthew, and I are all working on screens. We all sit down. We decided that we all needed these 10 columns. We go off, right? If we were using Vertica or Oracle, and Matthew decided to add 3 columns, Jerome and I's stuff would all break. We would need to call these columns out, make sure that they work, all that. Well, with Mongo, you don't worry about that, right? Anything that's not called doesn't matter, so you just add. Now, obviously, what happens is performance degrades. You have a limited SQL language. So what we've seen with Mongo over time is that it's really good for like a new app. The Mongo style too. I'm not just picking on Mongo, Couchbase. There's a lot of different database technologies out there that do that same kind of document store paradigm. And Oracle even has some. Some of these NoSQL Oracle services we've built. But they start to fall down once your app is up and running and you're trying to like tune it for production and you have a bunch of users on your system. That's when these ones start to fall down. So they're great for development. They become a little bit more challenging further down the cycle, right?
Yeah, you need some really good governance to use that. That's for sure. Yeah.
Right.
Thanks a lot for joining us for this segment of the Cloudology podcast. For our next part, please check out www.ateam-oracle.com. See you next time.